Hello everyone, this is the last chapter for fluid mechanics course, dimension analysis and similitude. And this chapter is not related with the previous chapters. Actually, we finalized the mechanics of fluid mechanics, and this is a separate chapter, and it is not unique for the fluid mechanics course. We will see some general terms related with dimension analysis, and we will see how to make modeling and similitude for experimental studies. Surely it is not unique for fluid mechanics, but in fluid mechanics we are using those a lot, so that we have this chapter in our course as well. In this chapter we will see how to understand benefits of dimension analysis, and we will also know how to use the method of repeating variables and understand the concept of similarity and how to apply it to experimental modeling. Initially, please note that in chapter 1 we went through with the dimensions, the basic dimensions, MLT, FLT systems. If you don't remember those, please go over the notes of chapter 1, and we will directly start with dimension analysis in this chapter. For the dimension analysis, let's start with an example. Consider this problem of determining the drag force on the smooth sphere of diameter d moving through a viscous, incompressible fluid with a velocity of u, so that the drag force may be stated as some unknown function of d, u, rho, and mu. This means that this drag force in this problem may depend on diameter, velocity, density, and viscosity. To determine the relationship experimentally will be very time consuming. You know that we need to make a controlled experiment, so that we need to keep one parameter varying and keep the rest of the dose as constant at each set. So that we need to make a lot of experiments in order to hold this condition. Due to this, we have to do lots of experiments and also draw many graphs. Also, such an approach would mean the use of many spheres of varying diameter and variety of fluids of different varying viscosity and density, and it is time consuming as well as expensive. But we will employ dimension analysis so that it will reduce the amount of work and cost. We will see how we will do it. Surely, while reducing the cost and time that we will spend, it will not give us the same result that we can obtain with this previous controlled experiments, but it will give us some ideas, some very important ideas about the problem. Think about again the previous example that we talked about the flow around the sphere, the drag force calculation. The above example will be formulated as a functional relation between only two dimensionless groups. Each group is called a pi term. It is not related with the mathematical pi number. It's just a name given pi term. So that we are arranging the variables into forms such that those arranged forms will be dimensionless. We call those as pi terms. From this previous parameters, we are arranging the parameters into two dimensionless groups. The first one is pi1 ft over rho u squared d squared. As you see, it is dimensionless. We have the check here. And the second term is rho u d over mu. It is again a dimensionless number. So that we arrange the variables into two dimensionless groups. In this chapter as well, we will see how to make those dimensionless numbers, but just for now, go through without knowing this. So that if we know that those two numbers are important for this problem, so that those can be used to represent some properties of this problem, we can just use those two numbers and we can decrease the amount of variables from 5 to 2, such that we can just keep one of those as constant and we can change the other one as variable, and we can just observe this relation of two variables. Suppose that the drag force is desired for conditions UA, dA, rho A, and mu A. Please note that those are just for spatial conditions. Dimensions group pi 2a can immediately be evaluated, and corresponding to this value of pi 2a, the value of pi 1a is read off the chart. Hence, note that fdA will be fdA over rho AU square A and dA square, and that was given as pi 1, so that pi 1 to be obtained from the graph, and this pi 1 should be multiplied with those variables in order to obtain f. Our analysis will be like this. And to establish such a useful curve, one may use a wind tunnel or a water tunnel. Surely we are making experiments. If the material that we are using is a liquid, we should use a liquid tunnel or channel. If it is an air or gas, we can use wind tunnel. And for a given sphere, the value of pi 2 may be easily and continuously adjusted by varying the free stream velocity u. Surely u can be controlled by us in those experimental sets. The force on the sphere is measured for each setting, and pi 1 may easily be calculated. That is how we can apply our experiments with less time, by having less time, and surely cheaper than the previous sets. Therefore, it saves time and expense, and a curve of dimensionless groups is established, which is valid for any fluid or any diameter of sphere in a flow within the range of pi's tested. So that this is the problem. How do we find these dimensionless pi terms, and how many pi terms can we obtain? To answer these questions, we need to have a look at Buckingham's pi theorem. This Buckingham pi theorem states that any relationship f depends on the varying different variables, where u1, u2, and uk are k physical variables which satisfy dimensionless homogeneity, can be reduced to a functional form of a different function, including pi terms, containing only k minus r independent dimensionless groups. K is the total number of variables in our problem, and we can drop that number of k to k minus r if we apply pi terms, and r being the rank of matrix of dimensions. For example, if we have all those three main dimensions MLT in our system, r will be 3. If we just have mass and length in our problem, if it is independent of time and we don't have anything related with time, r in that problem will be just 2. So that the dimension matrix will be formed by using each parameter's dimensions. And it's clear that the dimensionless groups employed are independent, not related to each other through algebraic operations. They should be independent from each other. Therefore, this theorem states that there can be no other independent group Hence, any other dimensionless group that one may propose will invariably be the one that can be developed by algebraic operations between pi terms. You can see if we make algebraic operations between pi terms, we can obtain different pi terms than we obtain from our problem. The pi terms that we have in our problem cannot be obtained from our set by using algebraic operations. And as I said, the rank of matrix can be equated to the number of fundamental dimensions exist in the problem. In civil engineering problems, we have just 3 fundamental dimensions. Depends on the system that we are using, either MLT or FLT. We can use any one of those. So that the first example, let's see how can we obtain those pi terms. The same example, the drag of sphere moving in a fluid. We have 5 variables. One is dependent, FD. The other 4 are independent. Please note that rho, U, D, and mu are independent, but FD depends on the others, so that FT is dependent. But in total, we have 5 variables. And having a look at dimensions, please note that the dimension of density is mass divided by volume, so that mass divided by L cube. Dimension of velocity, length divided by time. Dimension of diameter is just length. Dimension of mu is mass over length time. If you are not sure, you can use Newton's law of viscosity in order to obtain the dimension. And dimension of force is mass length over t squared. You can also obtain F dimension from Newton's second law, F equals ma. So that as you see, we have all m, l, and t exist in our problem. So that r equals 3, k equals 5. This means that we will have k minus r, which equals 2 pi terms as a result of our operation. After applying Buckingham's pi theorem, we will obtain 2 pi terms. To obtain pi terms, the method is as follows. Choose r-dimensional variables which contain MLT, but collectively, for this case, r is 3, so that choose rho, u, and d. In choosing those 3 variables, we are trying to have m, l, and t exist in the combination of those 3. These r variables are called as repeating or primary variables. These 3 variables, rho, u, and t, are repeating, and the other 2, remaining 2, which are ft and mu, are non-repeating variables. And we use them to non-dimensionalize the remaining variables. Actually, we will see more details in how to choose those repeating variables, but just for this instant, please note that we are choosing those 3 such that in the combination we will have m, l, and t exist. This is the first rule in determining repeating variables. So that we are arranging our pi terms like this. Those repeating variables will exist in all pi terms, and non-repeating variables will exist in just one of the pi terms. And we are writing the power of the non-repeating variables as 1 and the power of repeating variables as unknown, as a1, b1, c1, or a2, b2, c2 are given. And please note that those are unknown, but we can obtain because total dimension will be just 1. It will be dimensionless. Have a look at pi 1. We have rho to the power a1, u to the power b1, d to the power c1, and fd. And we know that pi 1 is dimensionless, means that it should have mass to the power 0, L to the power 0, and T to the power 0. And on the right hand side, we have the dimension of density, mass divided by length cube to the power A1. Dimension of velocity, L times T to the power minus 1 to the power B1. And dimension of diameter, L to the power C1, multiplied by dimension of Ft, ml over L times T to the power minus 2. And from here, we need to equate the power of m's of the left-hand side to the power of m's to the right-hand side. As you see, on the right-hand side, we have m to the power a1 comes from here, plus m to the power 1 comes from the power of ft. So that m to the power 0 should be equal to m to the power a1 plus 1. This means that a1 plus 1 is 0. This means that a1 is minus 1. Similarly, L to the power, have a look at the power of L on the right-hand side. We have minus 3a1 from the first term. From the second term, we have b1 plus b1. From the third term, we have plus c1. From the fourth term, we have plus 1. So that this summation should be equal to 0. Let's leave it now because we have two unknowns beside a1. And have a look at t. We have t to the minus b1 from the second term and minus 2 from the fourth term. This means that minus b1 minus 2 should be equal to 0. So that b1 is minus 2, and inserting a1 and b1 into the second equation, we can also obtain c1. And we can apply the same for p2. I will not go through all because it is not very much difficult. Please note that if we apply the same for pi 2, pi term 2, writing all the dimensions and applying the same operations, we can as well obtain the powers for pi terms, so that our pi terms becomes as like this, inserting a1, b1, and c1, a2, b2, and c2. Pi terms exist like this. So that, as you see, we obtained two non-dimensional numbers that we already saw at the beginning. This means that this problem can be formalized like this. Fd divided by rho u squared d squared should be a function of the other pi term, rho u d over mu. That's it. We can represent our result like this. If we would have more pi terms, the other pi terms should come into the function, and we need to leave the term which exists, which includes the dependent variable to the left-hand side. We need to leave this variable, which has the dependent variable inside, alone, and group the other remainings into the function. Okay, let's leave this video now, and we will go through with the next video soon.